Just to tell you again what we've done up to now. One of what we did first is to get this equation. So we have now a heat release source term. You see it's the unsteady heat release, and it's the derivative with respect to time, which comes in as a source term to this wave equation. So this can be used, for example, for combustion noise, because Q dot 1 can be associated to turbulence. Somebody was asking me, what about turbulence? Well, turbulence can produce heat release fluctuations. These heat release fluctuations will constitute a source term to this equation. We looked at the balance. We used one of the equations to get a balance for compact flames, because compact flames are very simple models. So you have a flame which is very thin here compared to the wavelengths, and we surround that by a volume. And by using this equation here and doing this reasoning, we got this result, which is here. The velocity on the downstream side minus the velocity on the upstream side is proportional to the flame transfer function multiplied by the velocity on the upstream side, the fluctuation here. So this is a rather simple relation for simple models. We are going to use that later on in the morning. And it can be actually written down in this very, very simple form, TB over TU minus 1 times F of omega V prime 1. And then we looked at the balance of energy, and we did the same reasoning as before, but now there is a source term, and when we do this calculation, integrate over an oscillation period, we find that the term that is driving has this shape, PQ dt. So it's the integral over the period. So if P and Q are in phase, this term is positive. If P and Q are out of phase, this term can be negative. It's very much like a swing. When the swing is going, if you put energy at the right moment, you go higher with the swing. So, and D is some sort of damping. And I told you that damping is more difficult to determine in the system, but we can have experiments giving damping. So and we looked at the balance of energy, and the balance contains actually 3 terms. One is the driving, something that could be driving, and this has to be bigger than the damping and bigger than what comes out from the fluxes of acoustic energy. In general, these fluxes will go out, so it will be easier to, it will be more difficult to reduce the instabilities. And this is very related to the Rayleigh criterion. The Rayleigh criterion tells you when P and Q are in phase, then you have a driving process. But you have to, this driving has to be bigger than the damping. So this is initially, now we have exactly the source term. We have its expression. It is given in an exact form. Actually here, there must be a gamma minus 1 over us. Yeah, there is gamma minus 1 over rho 0 c squared. Okay, so here we have exactly the balance of acoustic energy. So now there were a few questions that people wanted to ask. I answered a few. Yes. Yes.
I'm just trying to understand myself. Everything you just said, for the M flame, that means P is more in phase with Q, and Q is resonant frequency. Is that correct?
So in these flames, this is more an experiment on looking at the response of flames to perturbations. Some flames get the perturbation, but respond in with very weak fluctuations in heat release. This is the conical flame. It does respond. I will show you how the flame looks like when it is impinged by these acoustic waves. But the response, the gain is small. The M flame, on the other hand, is peculiar because you have a region of the M flame which is like this. And when the oscillation comes in, this region here of fresh gases, these two sheets can collapse and produce some sort of a region of unbound gases. And this is like a torus that is escaping from this flame. And this will produce a sudden pulse of heat release. It will produce a pulse of heat release at a later point. So you isolate a torus of unburnt products, or reactants, and it burns. And so there is a rapid destruction of material, of reactants, and this gives a pulse. And so this M flame, because of its geometry, is able to produce that. The V flame, we will see also later, it's an interaction between vortices which are shed from the lips of the nozzle and which impinge on the flame, roll up the flame, and produce a patch which is burning. So there are three processes here. And the most effective in terms of fluctuation, heat release fluctuation, is the M flame. Okay, but we will see that we will spend time on perturbed flames. This was just a sneak preview, just to look at the process. We haven't looked at it carefully. We will do that in not too long. Yeah.
But this is frequency dependent.
Yes.
You get the response only at
one frequency. But in fact, this works. The flames have a certain range of frequencies to which they respond. Right. This is one of the problems. Up to when do you have a response? How is you see the transfer function? You would like to know how it looks. Is it like that? What is this frequency here where nothing happens anymore? This is the gain. This is one aspect, and the other aspect is to have the phase. Is the phase doing something like that? What does it do? So these sort of experiments tell you what we are trying to do here is use concepts from controls. In controls, you're interested in the gain and the phase. And if you know gain and phase, you can say something about the process. The problem with combustion is that it's nonlinear. It's not so simple. It's not a linear system. The flame responds in various ways. The nonlinearity manifests itself because the sound that is produced is not only at 150 hertz, which was the incoming perturbation, but at all the harmonics. So definitely the system is nonlinear. Yes?
So the Regge criterion accounts for coupling between acoustic fluctuations and heat release fluctuations.
Yes.
Should there be something to account for velocity fluctuations as well?
No. Now, you have perturbations of everything. Velocity, the equivalence ratio can fluctuate, other things can fluctuate. But basically, the two main perturbations for flames are the velocity fluctuations and the equivalence ratio fluctuations that are received. And so what we are going to do, what we do is we determine the transfer function for velocity fluctuations, the transfer function for equivalence ratio fluctuations. And this is just we characterize the main perturbations, and these are the inputs, and the output is the heat release fluctuation. So you've seen the definition that I gave one of the transfer function, which is the most important, we feel. It's the heat release fluctuation divided by the average heat release, and the velocity fluctuation divided by the mean velocity. So that was the transfer function. So once you have the transfer function, then you have to, everything else is coupled. You know, the pressure field produces a velocity field. The velocity field will perturb the flame. The flame will produce a pressure field. The pressure field is produced by the wave equation here. You see, if you know the heat release fluctuations, you get the pressure fluctuations here. This is another way of writing things. You forget about that, but you have a jump condition which is given like that. And this is more of the energy, tells you about the energy. Yes?
You mentioned you could measure the transfer function. How do you do that?
You can measure the transfer function.
How do you do that?
So how is it done in practice? The velocity can be measured using laser Doppler velocimetry or a hot wire, or sometimes, for example, in a typical configuration. So you have here the your combustor, and you put the loudspeaker here. So this is a simple setup. And now what you can do is put two microphones here, just upstream of the flame. And let's assume that you have a conical flame here. You take these two microphones, M1, M2, and you produce the velocity fluctuation V prime here. The heat release, you take a photomultiplier. You put a filter, for example, for OH star, or CH star, or C2 star. These are chemiluminescence signals, either one. And this, for premixed flames, in the lean limit, this is more or less proportional. The intensity that comes out here is proportional to the heat release. It's not perfect. You can try to look at this relation at a given equivalence ratio, and you find out that definitely there is a relation. When the flame radiates in these bands, there is a strong heat release. When the flame doesn't radiate there is little heat release. This is good for premixed flames. We don't have something like that for non-premixed flames, but much of the interest now is in premixed flames. So, you know, there are limitations in the experiments. The experiments, you have one essential aspect of combustion is to know the heat release rate. This is, of course, when you have a flame, this is to get a certain level of heat release. Unfortunately, this is not measurable in a very in a precise manner, but this is sufficient. This is quite sufficient. So here you have the either a photomultiplier or a camera, and here you have the velocity. So you have everything for the transfer function. I will show results of that. You will see that later. Okay, let's move on. So now let me just show you a few slides which we will not look at in detail, but you can certainly try to look at them and redo the calculations by yourself. I think I don't have time to go through them. We are a little late even on the schedule. So you can ask yourself, you've made a lot of assumptions and to get these equations here. What about trying to make it a little more tidy and keep everything there and see all the effects? So for example, you can say, this is the mass, so no problem. But now I'm going to include also the tensor, the stress tensor, the viscous stress tensor. And I want to include also all the fluxes, the heat conduction fluxes. And then I know that combustion is a matter of changing the mass fractions due to the reaction rates. And I have also diffusion fluxes, and I have expressions for all that. And I want to keep everything there. So, and write down, nevertheless, acoustic equations. It is possible. It takes a little effort. you have to take into account now that the gas constant is variable, changes with W, because this is not a constant in combustion. And you know that the rule to get W, the molar mass, is this one. You have these inverses of all the mass fraction, the molar masses, and you take the mass fractions. So, and then you can write the temperature, you can derive something. The temperature depends on rho and yk, and depends on P, and depends on yk itself. So you can write all these expressions here, and you get this relation, which is here. You relate T to P and rho, and to the dyk's. When you do that, and you include that into the equation, the balance of mass, little by little, you get something which looks like that. So you have a bunch of terms which we didn't have previously. The heat conduction is here. This is the viscous stress. These are the fluxes coming out from the various species and so on. And this has to be together with the balance of mass and momentum. And you get something, you can get from that, from this set of equations, something which starts to look like a wave equation. It doesn't quite. You see, this is more or less like a Laplacian, but of the logarithm of P. And this is a d by dt square, d2 by dt square of logarithm of P. But you have 1 over gamma here. Gamma is not constant. C square over gamma is also appearing here. You have all these terms which were not there before. And then we have a term which basically is the combustion noise, which is here, associated with the non-steady heat release. In addition, you have terms which are just associated with the fact that you have changes in the molar mass. And this will produce sound. Because you have changes in, you change the molar masses, and so the volumes are changing, and this produces sound. And then you have a term which is aerodynamic sound. It's essentially the gradients of the velocity, double scalar products with the gradients of velocity. So, so the equation, a more complicated equation which governs pressure fields in reactive flows is this one. So this is given here. The heat release here, the heat release rate here can be written in this form if you have a simple reaction, a single reaction. And this is the dimensions of this heat release per unit volume. And W dot is the reaction rate. Okay, so how does one go? So you start recognizing that the combustion noise, oops, where is it? Yeah, here it is. This is the term which produces combustion noise, and this is the term which is associated with molar composition. There is a discussion by Sirby, and he was having an extra term, but these are basically the two terms that come in from these calculations. And if you want to get to the linearized equation like we did here, you replace logarithm of P by P prime over P, and this starts looking like a wave equation. And this starts looking like the term that we had here. The only difference here is that C square is now included in this term. If C square is constant, then you would have Laplacian of P, and you would recognize immediately the equation on the blackboard. This is aerodynamic sound. This is the sound produced by turbulent jets. It takes this shape here. And if there are changes in molar composition, there is a term coming in here. And there are other ways of doing the same sort of calculations. This is a second alternative, which goes along the lines that were used by Lighthill. Lighthill was the founder of aeroacoustic theory, the theory of the jet noise. So I'm just showing you the ways it's going. And again, what you find after a little bit of calculation is this wave equation. Here it's the other way around. And the term that is producing sound, that is producing the pressure field, is this one. So it's the time derivative of the rate of heat release fluctuation here. So you have a turbulent flame here, it will radiate sound, and this is the main term that produces that. And from that, it is possible to actually write, you see this equation here, that equation here, it is possible to actually write the pressure field if you are in an open medium. You have so the basic equation that we look at is this one. It's the Laplacian of P minus 1 over c squared dP by dt squared. And on this side, we have gamma minus 1. There is a minus sign over rho 0 c squared. And here we use a big key. Yeah, I should have used the same notation, but it's not. And so this is it. And so what is the pressure field that is radiated if you are in an open situation, if you are in unconfined situation? Suppose you have a flame here, sitting here, it's turbulent, it produces noise, and you want to know the noise that is produced here. We use what is called the retarded, potential representation, which tells you that the pressure field, for the solution of that equation in terms of the pressure field is the following. It's gamma minus 1. So we have this term. Rho 0 c squared is a constant, so we can keep it outside. There is 1 over 4 pi coming in here. There is an integral over all the source terms, the terms, the fluctuations that take place inside this volume are here. And you find them in the form of d by dt. So it's the derivative of q dot prime. So the fluctuations in heat release. These are located at a position R0. So R0 is this position here. And the observer is located at R. So you're here like that. There is a time delay because what is produced by this fluctuation here is heard here with a time lag tau, and tau is equal to the distance r minus r0 divided by the velocity of sound c. So we have here t r minus r0, the distance divided by c. This will be integrated over the volume because all the little sources will contribute, and also there is a decrease in terms of distance. We learned, you remember, that spherical waves diminish like 1 over r, and in this case r minus r0. So this is the basic expression, right? So how does one derive that? It's based on the theory, Green's theory. It's in electromagnetics. It's called retarded potential. Why retarded? Because you see, this is the retardation. This is a delay between the region where you have a source and the region where you are listening to that source. And so that's a general expression for the pressure field produced by these sources. It's a solution of that equation. I don't know if that's fine for you. Is it okay? So, of course, we don't like that. It's a little too complicated, but what we can do is assume that we are sufficiently far from the sources, that we are at a distance, and we listen to this combustion region. It doesn't take much to be in the far field. Just a few wavelengths and you are in the far field. For example, you are in my far field. You are sufficiently far from me. Even when I'm very close, you are in the far field. The near field is very small. And in the far field, R minus R0 can be just, you can neglect the size of the flame compared to the distance. So this is just R. And so the pressure can be represented as gamma minus 1 over 4 pi. We can just put R here. We have also gamma 1 over 0 C squared, C0 squared, and rho 0. And also the d by dt can be taken out of the integral. So it's the rate of change of the heat release. And here we have R0, so the sources, T, and the last term we can just assume that the sources are very compact, that the flame is very compact, the wavelength is large compared to the size of the source. Then you can just put here the distance R divided by C0 dV. So finally we got an expression. It's like a monopole. It's like the pulsating sphere of the other day, but in this case, what is producing the sound is not anymore an acceleration of the surface, but it's something which is like the heat release, the integrated heat release with a delay that is producing this. And you have you remember the other day for the pulsating sphere, we had an expression P is equal to rho 0. This was the volume acceleration 4 pi r times e to the I k r minus I omega t. So it looks a little bit like the same. So the flame acts more or less like a small, compact source. The heat release fluctuation in the flame will produce, its rate of change will produce the pressure field at a distance. So basically the theory of combustion noise is more or less included in these expressions. Yes? Yeah.
So when I stand behind a jet engine,
yes.
that's what I'm hearing.
No, you have many noise sources in engines. One of them is the compressor, the fan, especially when you have a very large bypass engines. The fan is very big and you listen, these are sound waves at a given frequency. So, so one source is the fan and compressor. The other source is the jet turbulence. So the jet engine produces a jet, and this jet produces turbulence, the mixing between the jet and the atmosphere. This produces turbulence, and the noise source is I've shown what it is. It's the scalar product of the gradients of velocity. Essentially, the gradients of velocity produce the noise. If you want to reduce the noise from jets, you have to reduce the velocity. The very high-speed jets will produce a lot of noise. It grows like the Mach number to the power 8. So this is a result of Lighthill. Lighthill, I think, was the first to get the fact that the pressure is proportional to Mach number to the power 8. So as you increase the Mach number, it makes a lot of noise. This goes in the subsonic regime. As you go supersonic, this goes to Mach number to the power 3. But in the beginning, Mach to the power 8. This is why these engines, the engines which have a very high bypass ratio, produce much lower velocities at the exhaust. You have a very big mass flow rate, a small velocity, and so the noise is much lower. So the modern aircraft have very little jet noise. So most of the noise comes from the machinery, the turbo machinery. And some of the noise, for example, at landing, can be combustion noise. So combustion noise appears when the other sources are disappear. It's a low frequency, so you will hear some of the combustion noise. But what you hear mainly is the turbo machinery, the very large fan. The jet noise has been reduced tremendously. This is why all these modern aircraft have much lower noise levels. Yes.
Though won't the machinery noise
Yes.
be narrow band while the jet noise be
Wideband, yes.
Okay.
Jet noise is wideband. It's a spectrum. The jet noise is like that. If you have a subsonic jet, it's like that, and the Strouhal number. So we represent things in terms of a Strouhal number. What is the Strouhal number? The expression F d over the velocity. So for example, you have a jet coming out from this nozzle here. This is the diameter. So you multiply the frequency by the diameter and divide by the mean velocity here. And typically the jet noise is maximum at Strouhal number of 0.3. So
now that's in subsonic.
that's subsonic.
Okay. Supersonic, is the Strouhal number different? Somewhere I thought I saw a paper that said it was 0.5.
It could be. It changes. It's of the order of something, yeah. But what goes on in the subsonic case, the pressure is going like Mach to the power 8. And when you go supersonic, the pressure will go like Mach to the 3. But at a very high level. The launchers, the spacecraft launchers, when they take off, have very supersonic jets, and they produce a very strong, very large amplitudes. The sound level is enormous. The scaling is, as you increase the size of the nozzles, you reduce the frequencies, and typically the main frequencies are in the 20 hertz, something very low frequency, extremely loud, and of course one of the problems is that the payload is fragile, and you have to protect the payload so that it doesn't vibrate to a point where it becomes useless when it's in space. So the comfort, we call that the comfort of the payload. It's is it comfortable in the vibration ambience that is produced? So anyway, let's close this parenthesis. It's all right. So this, I think, is the last slide of that one. Let me just go a little bit into combustion noise, because we now have the tools for that, and we can try to look at combustion noise. So combustion noise is not what we are at here, it's combustion dynamics, but it's of course very important to look at the noise radiated by flames and use whatever knowledge we got also in this case. So I'll do an introduction. The scaling will come out directly from these equations. What are the mechanisms of sound production? We have already seen this film about the perturbed flames. We are going to look at that in more detail. And And also, what are the confinement effects? Because the flames are usually not in the open. Of course, in the laboratory, the easiest way is to have a flame in the middle of a room, anechoic, and you measure the sound. But in general, the flames are confined. All right, so now we are interested in many, there are many possibilities. One possibility is the flame just radiates sound, and the sound doesn't change the flow or what happens here. Basically, we look at the flame dynamics. We have noise sources. We have already discussed some of the noise sources. You want to calculate the radiated field. Much of the engineering is to do about scaling. You know, how does it scale with the size, with the velocity, with the fuel flow rate? How does the noise go? And what are the spectral content? Where is the main frequency of the radiation? And of course, you want to control noise. The other situation is the situation where the sound field that is produced by combustion goes into an acoustic feedback and perturbs the flow, and you have a loop. So this is the topic of combustion dynamics. This is the main problem because in many cases, the noise, the fluctuations that are produced here by the flow that impinge on the combustion will produce fluctuations which will feed back, and this can be a loop, and the energy can grow, and the oscillation can grow. In fact, there are it's a little more subtle, because you have direct noise. For example, noise produced by this M flame. You see actually these torus of reactants which have not been reacted yet. This is typically direct noise, the noise that is produced by a flame. There is also indirect noise. What is this? Well, take for example temperature fluctuations. They are produced upstream and they go into a nozzle and they interact with the nozzle flow. What happens here is that this will produce pressure fluctuations. And here you have just temperature fluctuations without pressure. And there you get, and also backwards, you get pressure fluctuations. This is indirect noise. It's weakly coupled because this is produced by combustion, for example. Combustion produces temperature fluctuations. These go into the nozzle and they give a pressure field. This is a topic of my thesis. I was with my advisor, Frank Marble, we studied that. There is a famous paper of ours, which is well cited, which explains indirect noise. You know, this is another source of noise. You take temperature fluctuations, pass them through a nozzle, it produces pressure fluctuations. So at that time, it was not, when we did this work, it was not known and has been named indirect noise or entropy noise. Now, it is possible also that we have strongly coupled situations which lead to instability. You have the noise is producing a synchronization. You have an acoustic feedback, and this is strongly coupled. This is the main topic of what we are doing here. And there is also another possibility, indirect noise, strongly coupled. For example, here you have a stylized rocket, solid rocket. It produces vortices. These vortices impinge on the nozzle, produce pressure fluctuations, which come back here, synchronize the vortex shedding, and you have a system which is synchronized by this cavity here, and you get very low frequency in this case because these are very large boosters, and they vibrate because of this sort of mechanism, a mechanism of vortex shedding in solid rocket engines. So it's indirect because it's vortices which had no pressure field fluctuations impinging on a nozzle, producing a pressure field. The pressure field synchronizes the vortices. Of course, we are not going to study all that. It's too much. Just to give you an expression, one of the expressions that we got with the Frank marble was you have a compact nozzle here, you introduce hot spots, entropy waves, and you get here a pressure field, and this is the expression for the pressure field. But if you are interested in that, it's in the Journal of Sound and Vibration. There has been a lot of interest for that more recently. For a number of experiments have been done. A lot of work has been carried out in Germany. They started calling that Bremsstrahlung, acoustical Bremsstrahlung. So essentially, it can be due to entropy waves or vorticity. In fact, vorticity entering a nozzle produces pressure fields. So the question is, how much is indirect noise, how much is direct noise? It's very difficult to distinguish the two. I told you again at the beginning that there are many interactions taking place, and you see one of the interactions is entropy waves going into the downstream conditions, the nozzle, for example, and producing pressure acoustics here. So now what is the early work? Because this, the problem of noise generation by flame has been studied in early studies. One of the early experiment is quite beautiful. You make a soap bubble, you fill it with a mixture of fuel and air. And then you ignite that and observe the sound radiation by this bubble. And the early theory that was proposed, this was work by Thomas and Williams in those years, is that what happens is that it's the volume acceleration that is produced by the burning. You know, as you burn, there is volumetric expansion, and this produces a sound wave. And you get this expression. So this looks very much like the expression for the pulsating sphere. You remember we had rho zero, Q double dot. So this is the Q double dot that is produced by a bubble that is, I have always dreamed to reproduce this experiment, but never had time. But it must be fun, you know, you fill up a soap bubble and then you ignite it, and it produces a pressure wave, and you look at the signature of the pressure wave and try to verify that. Later on, in Hurley and Price did something related to that by actually looking at the heat release associated with the burning of the soap bubble. And to get the heat release, they actually related that to the volumetric rate of consumption of reactants. So you get an expression which also looks somewhat familiar, because you have this Tu over Tb minus 1 here, and this is the volumetric rate of consumption of heat. So there is, of course, a delay that comes in here. And then there has been a lot of work on this combustion noise. You can replace this volumetric consumption of reactants by SL multiplied by the change in surface area, which is here. And you can actually write down, so this was done by some Russians, and Clavin has worked on this combustion noise. You recognize something which looks very much like the previous expressions, and basically here you emphasize the fact that noise is produced when surface area of flame is changing. If you have a flame with a constant surface area, nothing happens. If you change the surface area, which happens due to turbulence, due to combustion oscillations, then you have, so this term is the important term. You can also follow Straley. Straley had a paper in the Journal of Fluid Mechanics where he derived this expression, which is also on the blackboard. Again, you see this expression is in red and yellow, just to emphasize that it's beautiful and it's also very useful. It tells you a lot about radiation from sound from flames. And basically it comes out from this equation here. You see when it's written in this form, there is a minus sign like there. And can be written like that. We've seen it previously. And there is relations between all these. It's possible to show that actually this Q here can be represented like that and can be related to the Q dot prime here. And so this and that are very much of the same. You see this is very, and the rho U over rho B is like TB over TU. So there is the older theory and the more modern, this is more modern, are related. You see these two things are related. There is a relation here. And now in acoustics, when you want to calculate the power, which is the most interesting thing, you have to do correlations. So basically what you do is you correlate the pressure and you take the average, P prime square, average, rho 0, C 0, so that's the flux, multiplied by a sphere, so you eliminate the radius, and this is basically the expression which allows you to do some scaling. This is typical of what is being done in acoustics for evaluating sound levels. So what you have here is the source terms at two positions. There is a correlation that you have to take. It's a double integral over the volume for the first source term, the second source term, and then you have to take this average, the ensemble average. And it's convenient to change coordinates. You take the distance as one of the coordinates, and you take the other one as one of these. Can be written like that. I'm sorry, I'm going very fast because this is not really the main topic here, but just to give you an idea, and you can go back on these equations and look at the references. And so what you really want to do is to get some scaling. For example, how does that scale with the mass flow rate of fuel? How does it scale with the heat released per unit mass of fuel? What about the volume, the correlation volume? And you find something like that. This is due to Tim Leuven and one of his students, Rajaram. And they arrive to an expression which contains the main frequency, we will see what it is, of this radiation, some sort of efficiency function. It correlates with the mass flow rate to the power of 2. And this is the heat release per unit mass. Typically for propane, it's 42 megajoules per kilogram. And for hydrogen, it's how much? 1 kilogram of hydrogen, how much does it produce as a number of megajoules? It's very important. It's 120. So hydrogen per unit mass gives 120 megajoules in terms of heat release. So here you have an expression that gives you the scaling of this. So we will see how that comes out in plots. So for example, one is to know what is the frequency of this sound radiation. And Leuven and also previous work by Béliard and Truffaut in Marseille were showing that basically the main frequency scales very well with the velocity coming out, the mean velocity, divided by the length of the flame. So the frequency is U divided by the length of the flame. If U is, let's say, 10 meters per second, you have a turbulent flame, and LF is, for example, 20 centimeters. Well, you have directly the frequency right here. And you see the many experiments indicate that more or less this is well satisfied. The second one is this scaling in terms of fc square. So you have the velocity u square coming in here. The length is on the floor here, lf square. It scales like the mass flow rate of fuel to the power 2, and h also to the power 2. And you see that there is a cloud here, so basically the scaling is reasonable. It's not perfect. The evaluation of the sound levels is really more difficult. It's when you do just scaling, you're not doing calculations here. You're doing just dimensional analysis. You get something which is reasonable, but not quite. It should collapse if everything was perfect. Yes.
So what's the source of the spread in the data here?
Perhaps the scaling is not quite fine. Perhaps the measurements are not quite done in the best possible way. You reduce the problem to a very simple dimensional analysis. For example, the Mach to the power 8, it's the same. Basically, it is satisfied, but you have, it depends on the jets, it depends on the upstream conditions, it depends on the type of turbulence. So there is a limitation, but nevertheless, it's useful because you would like to know how much sound will I get from this flame. You take something like that, you will get. Now, decibels, if you have 6 decibels more, it's a lot, It's not 6 decibels is twice the pressure fluctuation. So it is. I'm not sure this is the best scaling. I was just showing one of them. This is due to these people as well as especially Leuven and Rajaram. Yes.
So this is more likely to be due to the assumptions and scaling than the errors in measurements.
Yeah, you reduce. You start with something which is basically quite reasonable, and then the whole problem is to represent this correlation here, the spatial correlation, to represent that properly. And there you do your best. You try to make the dimensional analysis as close as possible to that. Yes?
Does that spatial autocorrelation assume that the flame size is much less than the wavelength of the sound?
In this case, we were, do we assume a compact flame? I think it assumes some compactness that the flame, but this is really satisfied. Usually the flames are small and the wavelengths, the frequencies are, this is low frequency. This is essentially low frequency sound. Combustion is low frequency. I make a long story very short. I'm sorry for that, and because it's not the central topic. It's just, it's too bad not to speak a little bit about combustion noise, but it's not, we don't have to spend too much time on that. It's a topic of its own, but you have a flavor of what is done here. So you see, you replace something complicated by something which is rather crude here. So it's, if you are clever, you get a good result. If you are in between, you get something in between. And if you are not, there is a little bit of art in doing that. So it's credible, but the result is like that. Okay, so let me now go to something which is closer to what we want to look at, but which is also of interest to noise. It is the flame perturbations. And we have already actually looked at, I told you how we do the measurements. Of course, you have a flame, you want to analyze that flame and analyze the heat release fluctuations. This can be done, as I indicated before, using a filter. You look at CH star, you have a photomultiplier, or you look at OH star. So Q dot is proportional to the intensity. On the other hand, modern technology allows you to get the area for simple flames. It is possible to actually look at the area that you are producing, and if you know the area, you know the dA by dt. And we've seen that dA by dt is producing the pressure field. So you can measure using a camera the area, and from the area you can calculate the heat release rate. And using microphones, you need microphones, and now we can do that on simple flames. So the device that we have been using very extensively to study this phenomena is this burner. You have a loudspeaker here, you have this rod, there is a nozzle here, and you can produce flames, conical flames, M flames, which are stabilized on the lips and on the central rod, the V flame, and multiple conical flames. We also did a lot of studies of what happens to little flames which are on the matrix, because many processes use such systems, and they have noise problems, they have oscillation problems. And so you see, for example, what does the conical flame, if it is impinged by acoustic waves, you can have many shapes, you can produce something like that, cyclically. If you have the M flame, you see, it produces this, that, you get to this point, and finally you get a torus. The V flame takes this very special shape, and you see that there is roll-up taking place, and the vortices come from the lips of the nozzle. If you have the M flame, the little flames, the conical flames, the collection of conical flames, they go up and down. So they go up, they produce these little bubbles. The bubbles are detached, they are shed, and they burn at a later point, and the flames go down, and the process repeats. You go here, and then here, and again. And we also studied the situations of interactions. Put a plate. You have a flame, and you have many possibilities. Actually, one of the possibilities is that the flame is still stabilized on the lips and interacts with the flame, like that. But the other possibility is to have a flame which is stabilized as a flat flame, detached from the lips. But we studied this one. So, for example, in the low frequency with the conical flame, using Schlieren, this is what you see. So what we use as a frequency, a reduced frequency, is omega times the radius of this burner divided by the burning velocity of the flame. And this is the angle cosine alpha 0, the half angle of the flame. So this is a 4-color Schlieren. It's nicer than a black and white Schlieren. It gives you also an indication on the gradients, the way the gradients are there. So it is sensitive, of course, to the refraction index, which itself is changing with the density. So this is the cycle that is produced here. So you have the flame is moving in this way. This is in the low frequency case, omega star is equal to 5. These are the conditions. As you go to a higher value of omega star at a higher frequency, you start getting what Daniel Durox called pagoda flames, like a pagoda, more or less, or a Japanese temple flame. If you are in Japan, it's a Japanese temple. If you are in China, it's a pagoda flame. So you see the flame takes this shape and like that, and you have this shape and goes back to this one and so on. So you see these waves. I have some films, I can show you this. And so once you have that, you have you can look at the pressure field that is radiated. So this is the waveform itself that is recorded by a computer. You can look at the area. You can extract the area itself. And if you look at the rate of change of the area, it matches that of the pressure. You can look at also the intensity of the radiation, and this again can be compared to the pressure that you get. So basically, these flames are not very loud. We've seen that in the film previously, but you certainly have these expressions between the pressure and the surface area, and also the intensity and the surface area rate of change. So this definitely confirms some of the expressions that I've shown. This is the case of the M flame, and I told you the mechanism that is producing the sound is this the reactants which are being shed and which burn at a later point and send a pulse. This is done for the M flame. You can again compare the pressure and the rate of change of the area. And the pressure has a peak when there is a strong rate of change. For example, suddenly the area reduces strongly, and there you have a pressure peak coming in. Of course, you have to take into account the delay between. You have to shift the pressure waveform to compare it to the dA by dt by the certain amount of delay. You take that into account. You know the delay. This is a much louder process here. You see, and basically it's the burning of this that provides the radiation. In this case, you have not only the main frequency, but a lot of harmonics. You see, the spectral density shows you many harmonics. Let's stop here for 15 minutes, and let's come back at 11:15, 11:16, all right?